Chris the Carpenter here, RocketBrandStudios.com, and this is my CNC mill. I've actually had a lot of people ask me questions about this and ask me to make CNC videos, and so we can consider this an introductory video to exactly what these machines are about, what this particular machine is about, and just kind of give you an overview of what's going on here. So, first and foremost, this is a 3-axis machine, which means this cutter head can move in X, the table slides back and forth for Y, and then the whole cutter head can go up and down for Z. So that's 3 axis. I actually have a 4th axis, and I'll show you that in a second, and a 4.5 axis, and I'll show you that in a second. But at the end of the day, a piece of material is clamped here. A design file goes from design software into what they call CAM software, where you tell the machine how big the bit is you're going to use, cut the inside of this, the outside of that line, you know, that kind of thing, cut in this order, etc., etc. And then that CAM software spits out what they call G-code. G-code is basically just a list of coordinates, X this, Y that, Z this, and those coordinates go from the computer to the stepper motors and allow the machine to move. Okay, so let's take a closer look at exactly how this machine works. These are called linear bearings. These are actually called fully supported linear bearings because they have this backbone down the length of them. These are called ball screws, and there's actually a very fancy nut on each of these, and each of these gets spun by the stepper motor. Now, I purchased all of these as a set. So I got the X bearings, the Y linear bearings, the Z bearings, and all 3 ball screws, lead screws, all in one kit from eBay. And then this entire machine was built around those dimensions. As you can see here, here's the 2 linear bearings themselves sliding on the rails. This is for the Y-axis, the table. And we scoot around here, you can see the bearings, you know, sticking out the back. Now, the spacing of these 2 bearings, based on the size of the table, was just a simple calculation of how much travel I wanted versus how wide I could make those to keep the table stable and not rocking. You can see the same thing here. The X bearings are sitting there, and then there's a total of 6 Z bearings, which are considerably smaller, so I use actually more bearings to stiffen it up a little bit. You look in there, again, another lead screw, another ball screw with the stepper motor on top. This is what's called a stepper motor. It spins, but it spins as a series of steps. In my case, 3,200 steps per revolution. You can see I've got one on X, Y, and Z. There's X tucked around there. You see a little coupler and then the screw. So a given number of steps equals a given amount of travel. And the software that runs this machine knows how many steps equals how much travel, and that's how it knows basically where it is. These steppers are run off of stepper drivers. You can see them in there as well as the big power supply, dial indicator. And then finally, this is a parallel port breakout board. This is a parallel port plug from an old PC, and full-size PC that actually has a parallel plug in the back. You cannot use a laptop and an adapter. And that's where all of the control wires are broken out into the drivers that eventually run the stepper motors. This is my main cutter head. That's a tag spindle. You can see the bit underneath. And you can also see I milled some gears there to gear the router down. If you're going to use a router in your machine, don't. They're way too fast. You got to find a way to slow them down. So I have a speed control on this router that cuts it down to about 10,000 RPM. And then with the 2-to-1 gearing there, I'm down to about 5,000 RPM. You can see the dust collection It goes up and around and into my dust collector. That gets removed when I'm doing aluminum, and instead I use a mist cooling system to spray on the bit to keep the bit cool while milling aluminum. That bucket is full of coolant right there. Previously, I used this guy. That is my old router clamp. It's all polycarbonate that I milled out to hold the router directly, and that was a pretty good router holder. But again, now that I have this gearing, 1,000 times better. I also have a what they call a fourth axis, or a rotary axis, and I use this for cutting gears and splines, and it also allows me to rotate material on the table to get to, say, all four sides of a piece of square stock. So this whole mechanism gets bolted to the table and moves with the table, allowing me to make cool stuff like that. And finally, the construction of the actual machine. My advice to you, if you're going to make a CNC, is you got to do it like you mean it. You can't go in halfway. You know, if you spend $500 to build a machine, you're not going to have a usable machine until you hit about $1,500, $2,000 realistically. And that money basically goes into big motors. This machine will eat aluminum alive. It'll go through 1.5 inches of aluminum and not even think twice about it. And it's because I have an incredibly heavy, solid, rigid machine. I've got big motors running it. These are 570 ounce-inch motors, plus the gearing down of the threaded rod. The machine itself is physically heavy. All of the framework is 1/4 3/8 thick solid steel. Everything is welded. When I built the machine, again, I built everything, I designed everything on paper based on the dimensions of the glides I had, of the bearings I had, and the screws. So everything was designed literally for whatever that day's welding was. I would figure out my math for the outside frame, and then kind of build off of that. But the main thing is rigidity, 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 and you got to figure in some adjustment. So every single hole on this machine that a screw goes through is oversized. So that allows me a little wiggle of adjustment. So when I welded this, I got it really, 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 really incredibly close. As close as I could get without a proper welding table and without proper welding fixtures. But with those oversized holes and allowing myself a little bit of play on each axis, I was able to dial everything in, even with basically a homemade frame that was off a little bit. I think at the end of the day, I didn't have to shim anything more than about 3 business cards thick to get it into square, into plane. So there you go. There's your quick overview. If you want to hit the eBays to kind of start figuring out what this is going to look like, your search is fully supported linear bearing ball screw. That'll bring up kits where you can get all 3 axes together. The stepper motors, you're going to want to look for, the eBay search will be like 3X NEMA 23, which refers to the size of the motor, the bolt pattern of the motor actually. Like I said, mine are 570 ounce-inches, and they're plenty for a machine like this. The search for the motors is Long's motor, or NEMA 23, or 470 ounce-inches, 570 ounce-inches, those will all bring it up. Fourth axis, eBay searches CNC fourth axis. You'll find that. And then, of course, I run everything using Mach 3, which, unless you're a Linux user, if you're a Windows person, Mach 3 is the standard, and it's awesome, and you can configure it to run basically any machine you want. So, so there you go. There is my quickie overview of this machine and everything that sort of went into building it. And I hope this at least gets you moving on some Google searches of your own, and hopefully you can start digging out from the internets the information that you may need to build your own. So again, Chris the Carpenter, RocketBrandStudios.com.